Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In this episode we are going to add materials to the low-level renderer. As I explained briefly in the previous episode, a material defines the look of an object when it's being rendered. I'll start this video by explaining how a material can be represented as high-level and low-level data structures. Then we continue by implementing materials for the Direct3D12 renderer in Primal Engine. Previously, we started working on the render item, which is a data structure that functions as a link between the geometry, the entity that owns that geometry, and the materials that are needed in order to render that geometry. It basically connects everything together that a low-level renderer needs in order to render an object. We already defined the high-level render item in our code. However, before writing the code for the low-level render items, we really need to implement low-level materials in the renderer. So as we can see here, at a higher level, a material is just a list of textures and the shaders that will take the geometry, sample the textures, and finally output the pixels on the screen that belong to that object. In reality, we can define a lot of properties for a material. For example, the material type, blend mode, refraction index, and much more. However, let's start with a simple material model with just one property, which is the material type. The material type, together with shaders and textures, will define a high-level material that can be used as an input for the low-level renderer. From this information, we can create a block of memory that contains the material type, shader flags, the root signature, number of textures, and the IDs of the shaders and textures. Additionally, it will also contain an array of descriptor indices that will be used in the shaders to index into the descriptor heap when sampling textures. The details for this will become clear later when we write our shaders. However, for now it's important to note that the shader flags is just a 32-bit unsigned integer that has the bits that correspond to each shader stage that is used for this material set to 1. Using these flags, we can know how many shaders are used as well as which shader stages are used. The same shader code can be used for different materials, and therefore also the same root signature can be used for multiple materials. Because the material type and the set of shaders will determine the data that is available to each shader stage, we can use them as a key to a set of root signatures. That way we don't have to create a root signature for every single material. Looking at create render item function, we see that we need to have a material in order to be able to create a render item. Let's add a function that will tell the engine to create a material. In order to tell the engine what the material is, we need to have a material init info. I'll add it in the renderer.h. This structure describes a high-level material, so it needs to have a material type for which we need to create an enumeration. For now, we'll only use opaque materials, but later we can define other types like transparent, unlit, clear coat, and so on. The next field in material type is texture count. As I mentioned before, using textures is optional, so this number may be 0. Next is the array of shader IDs. I'll add an enumeration for shader types, so we know how many elements we need for shader IDs. Here we'll have an entry for each shader stage, although obviously many combinations of shaders are prohibited. For example, we couldn't use a vertex shader and a mesh shader at the same time. However, this array is simply intended to contain IDs for any valid combination of shaders. Therefore, we need to initialize it with invalid IDs, so that later we can determine which shader stages are used by checking if an element in this array contains a valid shader ID. And finally, we need a pointer to an array of texture IDs, if any. We can use this structure as a parameter for creating materials. We already have our shader IDs, so we can add those. We don't have any textures yet, and the material type is opaque. When the material is created, its ID will be returned to us, which we can use for our render item. Now we can call createResource with this material information to create the material. Next, we need to write the code that actually creates the material. This is quite similar to creating a geometry resource, so we need to add createMaterialResource and removeMaterialResource functions here in content2engine.cpp. Let me also quickly document what needs to be in data, since we are using a raw pointer. I could have just said that we need to use a material init info, but that would be too easy. After making sure that data is not null, we can call a renderer function, which in turn calls a low-level renderer function that will eventually create the material. We also add the remove function. Now we need to add these functions to both the high-level and low-level renderers. Similar to what we did for submeshes, we need to expand the graphics interface in order to be able to connect to the low-level renderer. After doing so, we can use the function pointers to call the corresponding low-level functions, which we are going to write next. Here I'll create a namespace for materials where we put the add and remove functions, as well as any other public functions and data structures that have got to do with materials. Before implementing these functions, I'm going to describe the data that we are going to put into the block of memory for a material. This is the same as I described in the slides earlier. So we have material type, shader flags, root signature ID, number of textures, shader IDs, and optionally an array of texture IDs and descriptor indices. Next, we need to add the containers for the material data. We need an array that will hold the root signatures. Because root signatures are in general used by multiple materials, we need to map materials to an index in this array. We can create a key using the material type and shader flags. We also need a free list that holds pointers to each material's memory block. And finally, we need a mutex for synchronization. When we want to create a material, we need to have a pointer to the buffer where we write the material information. Then we lock all material data, create the low-level material using the buffer, and then add the pointer to the materials list. Obviously, we don't have the code that actually creates the material yet, but we'll be writing that in a minute. First, let me quickly write the remove function. Here we just lock our data and remove the material pointer from the list, which will free the memory buffer. Note that we don't remove the root signature because it could be in use by another material. We'll only release the root signatures when we shut down the renderer. Now, for the material memory block, we are going to implement something very similar to what we did for the geometry hierarchy. That is, we will have a class that's used to read and write to a block of memory using a specific format. I'll call this class the 3D12 material stream, which is again used only internally and can't be copied or moved. Let's start with a simple use case, which is when we already have a block of memory that contains the material information and we just want to read from it. In this case, we simply initialize the member variables. These are a raw pointer to the material buffer, a pointer to the texture IDs, and another pointer to the descriptor indices within that buffer. And we also need a pointer to the array of shader IDs. Finally, we just copy the root signature ID, texture count, material type, and shader flags from the buffer. We still need to define our enumeration for shader flags, so let's do that next. I'll put it just before shader type enumeration in renderer.h. We can initialize the buffer pointer in the constructor. In the private initialize function, we just read the data and set the pointers to the corresponding offsets within the buffer. First, we can read the material type, and in order to easily set the offsets, I'll define some constants depending on various data types that we are using. So shader flags come after material type, followed by root signature ID. The next constant that we need is the location of texture count within the buffer. Using these constants, we can get the shader flags, root signature ID, and the texture count. The array of shader IDs starts right after texture count, and finally, depending on whether or not we have any textures, we can set the pointers to the texture IDs and the descriptor indices. To calculate the pointer to texture IDs, we need to know how many shader IDs we have, and as I discussed earlier, that's determined by the number of set bits in shader flags. That means that we need to count the number of bits that are set to 1 in the shader flags, which we can do using an intrinsic function. We can look up intrinsic functions on this website. The one that we are interested in is called MMPopCount U32, which, as you can see here, counts the number of bits set to 1 in a 32-bit unsigned integer. We can also see what the operation is in pseudocode, and there is even performance information for various Intel architectures. Okay, let's use this intrinsic to count the number of shaders. Also note that if we don't use any textures in this material, the texture ID and the descriptor index pointers will be null. Now I'll add a constructor that will allocate a memory block and write material data to this buffer in order to actually create a material from material init info. Therefore, we need a reference to a unique pointer that will point to the allocated buffer, and of course we need the init info. First thing we do is to look for valid IDs in the array of shader IDs and construct the shader flags from that. Then we need to calculate how much room we need in the material buffer. This is simply a sum of all data sizes. For the shader IDs, we need to multiply the size of ID type by the number of shaders that we just calculated. And for texture IDs and descriptor indices, we need to multiply by the number of textures. Now we can allocate a block of memory with this size and start writing our data to this buffer. This is basically the reverse of what we did in the initialize function. For the root signature ID, we need to write a function that will create a root signature. We'll do that later, but let's finish writing this constructor first. We can call the initialize function to read the data in member variables and set the pointers to which we can write the shader and texture IDs, as well as the descriptor indices. Of course, we only fill in texture information only if this material uses textures. And finally, we copy each valid shader ID to the array of shader IDs in the buffer. We also assert that the number of shader IDs is the same as the number of set bits in shader flags. Now for the descriptor IDs, although we don't have texture content yet, we can write a function that will get the descriptor indices. So let's pretend we can import textures and add a namespace here for them, like we did for materials. Here we'll also have an add and a remove function. In addition, we can declare a function that will take a list of texture IDs and return a list of descriptor indices. All we have to do now is to write this function. When we create textures, they will be added to a free list of D3, D12 textures, and we also need to synchronize it using a mutex. In get descriptor indices, we lock the texture data and simply copy each descriptor index to the array of indices. Now we can call this function in our material constructor. This is where I'm going to stop for today. In the next video, we are going to continue and finish this code for low-level materials. As always, thank you so much for joining me, and I'll see you in the next one. Cheers! Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!